Uh, Good evening. This is Professor David J. De Los Reyes. It's December 24. Okay, the time is around 11:26 p.m. here in Los Angeles, California. Okay, my topic tonight will be the continuation of my subject matter differential equation. This is now lesson number 39. Okay. This is lesson number 39 on my differential equation, DE39, second order differential equation. I will now be giving you example number 3, another variation of a problem that falls under second order differential equation. Okay, let's proceed. I just checked my camera. To illustrate example number 3 under lesson number 39 on my differential equation course, the given differential equation, I will try to read the given problem. D square y over dx square minus 6 times dy dx plus 9y equal to 0. That is the given second order differential equation. SODE. Second order differential equation. And the initial condition is there are initial conditions given, that is the value of y is equal to 1 when x is equal to 0. So we are having a problem that asks for the so-called particular solution. So the requirement of the problem is what will be the particular solution. Why particular? Particular because we are given initial conditions. Okay? And as an additional requirement for the problem, plot the graph of the resulting particular solution. We will plot the graph. What kind of graph it is? Okay, could we visualize it? Okay, let's proceed with the solution. As always, under second order differential equation, we got a substitution here. That is, we will let y equal to k e raised to mx. That's a standard operating procedure under second order differential equation. That is the required substitution. Initially, okay. Let's try to compute for dy dx. Dy dx, it will be the differential of this if we try to take the differential of y equal to this. So if we now try to take the differential of y, it will be k times e to the mx times m times 1. Okay? Simplifying this one, it will be km e raised to mx. That is dy dx equal to km e to the mx. That is after the so-called differentiation. Since we are to need the so-called second order, what we call this d square y over dx square, we will take again the derivative of the first derivative. So what will come out will be d square y over dx square. We needed this one for us to bring back to the original second order differential equation. So taking the derivative of the first derivative, and that is actually equivalent to d square y over dx square, and this should be equal to the derivative with respect to x of km e to the mx. K is constant, m is constant, the product of two constants will still be constant. Okay, we bring it out, so it will be km times the differential or derivative of e to the mx. Exponential function, e to the u, it will be e to the u times du dx. So this will be e to the mx, and the differential or derivative of the exponent, it's a constant times a function, so it will be that constant m times the differential of that function. That function is actually x, and we are taking the derivative with respect to x, so this is supposed to be multiplied by 1. So d square y over dx square, if we try to multiply all these ones on the right hand side, it will be km square e raised to mx. So we are now given y, we are now given dy dx, and we are now given d square y over dx square. Okay? We will take these three values here, bring back to the given original second order differential equation. So I place it here, substituting. If we now try to substitute the three values y, dy dx, and d square y over dx square back here, what will come out will be km square e to the mx minus 6 km e to the mx plus 9k times e raised to mx equal to 0. Okay? We try to simplify the resulting equation after the substitution. Because there is a common factor, we must have to eliminate the common factor. The common factor for all the terms is actually k times e to the mx. We must have to eliminate this for the resulting equation to be simpler. Okay? We could do that. We could do that without violating any rules under algebra. So we will multiply the resulting equation by the reciprocal of k e to the mx, and the reciprocal is actually 1 over k e raised to mx. If we now try to expand this one, okay, this k here cancel with this k here, and this e to the mx cancel with this e to the mx. So what will come out on the first term will just be simply m square. K and e to the mx will be gone, right? For the second term, this term here multiplied by this k here will disappear, and this e to the mx will also disappear. Okay? So what will remain for the second term will be 6 times m. This is 6m. And the third part will be, this k here will disappear, and this e to the mx will also disappear. So what comes out on the third part of the left hand side will be plus 9, and this should be equal to, for the right hand side, this is 0 times 1 over the k e raised to mx. Anything multiplied by 0 will still be 0, so the right hand side is 0. I haven't placed this one the last time around, but under second order differential equation, the resulting equation is actually, that is termed as characteristic equation. We term the resulting equation to be a characteristic equation. Characteristic meaning it's the equation that involves the exponent of the resulting solution. And that is actually quadratic. Okay? So if we now try to compute for the value of m, we will use our knowledge of algebra. You could use factoring by inspection, or factoring, solution by using quadratic equation. But since we can factor out this by inspection, okay, we will not resolve to the solution quadratic equation. Okay? The possible factors of m are actually m and n. And the possible factors of plus 9 are actually 3 and 3. And if we try to check the value of the middle term will be minus 3 times m is minus 3m. M times minus 3 is also minus 3m. So if we try to take the sum of these two negative values, that will be equal to minus 6m. And this minus 6m is actually equivalent to this. So the resulting factor out will be a quantity m minus 3 times the quantity m minus 3, and they should be equal to 0. Okay? Taking its factor and equate it to 0, m minus 3 equal to 0, m1 now will be equal to 3, that is after the transposition. We will take the second factor, which is still m minus 3, and we equate that again to 0. M2 now, meaning the second value of M, that is after the transposition, will still be equal to 3. So what comes out for the value of M1 and the value of M2 are actually equivalent. They are both 3 and 3. So this falls under the condition they are equal, right? And real. Why real? They don't have the so-called J value. It is just a plain number plus 3, okay, without the J thing. Without the J thing, we call the resulting number to be a real number. So the resulting values of M1 and M2 are both real and equal, and this should fall under case number 2 under the so-called solution of second order differential equation. This falls under case number 2. The resulting roots are actually equal and they are both real, so the solution should fall under case number 2. I will check my camera. Okay, still fine. So if we now try to bring out the general solution under case number 2, for case number 2, this should be y equal to q1 e raised to m1x plus q2 e raised to m2x. But since m1 is equal to m2, we could simplify the resulting general solution. If this is m1x, and we will replace this m2x by still m1x because they are the same, right? What will come out will be, there is a common factor e to the m1x for the first term and second term. So we will factor out that e to the m1x times the quantity q1 plus q2. And again, to further simplify the resulting general solution, we will let q1 plus q2 to be another constant, okay, which is different from q1 and q2, and we call that k3. So the resulting general solution, okay, for the roots m1 equal to m2, they are both 3, the solution will be equal to k3 e raised to 3x. This is still a general solution. Why general solution? Because for the meantime, we do not know the value of k3. The problem is asking for the particular solution, so it's a must that we should compute for the value of k3. And to compute for the value of k3, we will just apply the given initial conditions. The given initial condition is that y is equal to 1 when x is equal to 0. Okay? So applying the initial conditions, y is equal to 1 when x is equal to 0. Okay? The significance of this is that if we apply these conditions here, we could solve for k3. So going back to the general solution, we will apply this initial condition and we could compute for k3. So 1 now, we are following this, equal to k3 e raised to 3 times 0. This 0 here refers to x and this one here refers to 1. Okay? Simplifying this one, no magic, right? 1 is equal to k3. 3 times 0 is actually 0. Okay? And e to the 0 is actually equal to 1, right? The value 2.718218183 raised to 0 power is equal to 1. That is if you try to use your scientific calculator. And we know that any number raised to 0 power is equal to 1. So e to the 0 will be 1. So what comes out now will be 1 equal to k3 times 1. Solving for k3, this is 1 and 1. So k3 will be equal to 1. So the unknown k3, which we needed to compute for the particular solution, will be equal to 1. So going back to this, we will place the computed value of k3. So what will come out will be y equal to 1, which is k3 times e to the 3x. 1 times e to the 3x is just e to the 3x. So the particular solution of the given second order differential equation is y equal to e raised to 3x. That is our particular solution. And the problem is also asking for the the graph of the resulting equation. Could we visualize it? What will be the importance of this in the so-called in actual things? Maybe in the design of those flying missiles, maybe the graph will be something like this. It's an upward motion, something like this. So there was actually a relation of differential equation for the design of those flying things. That's the importance of the differential equation. So if we now try to plot the graph of this, it's easy. I just need 3 points on the graph. When x is 0, y is 1. That is the initial condition, right? When x is 0, y is 1. It is this point here. And if we try to increase the value of x going to the right, when x is 1, okay, y will be e raised to 3 times 1 is actually 3. And a raised to the third power, that will be approximately 20. So when x is 1, y is 20, this side here. Increase a little bit to the right, when x is 2, I computed using the calculator, y is actually 403. So it is actually abruptly increasing upward. So when x is 2, this is 403. Okay? Maybe if you try to increase more the value of x, it will go up something like this. Sorry for that one. It will go up something like this. And what's you call this? What will be the most significant equivalent of this? It seems it's a missile going up. Okay, it's a missile going up. And the graph of this is actually y equal to e to the 3x. That's the importance of this differential equation in real life, much more on the design of those flying objects. Y equal to e to the 3x, the graph is something like this, abruptly going up. That's it, guys. The particular solution is this one, and the graph is this. I will try to erase this one. I will try to show you the graph in actual thing, you know. You now know why if they try to fire a missile going upward, it is something like this. This will be the y-axis, this is the x-axis, this is the y-axis. When x is 0, this is the point. When x is 1, it will become 20. When x is 2, it becomes 403. Maybe when x is equal to 4, it's going up. So the graph is actually this. And the equation of this is y equal to e to the 3x. This is 0 and 1. This is 2 and 20. This is what you call this 2, and this is 403 already. So if you try to notice it, as you increase x going to the right, the rise is actually very steep. It looks like a missile par going up. That's it, guys. If you try to grab the part of this, it is something like a missile going up. Right? Oh, that's it. That's the significance of second order differential equation. So it will be a problem of those designing missiles. And the equations they are using is actually differential equations. Oh, that's it, guys. An example number 3 under second order differential equation. At least I have shown you the significance of this second order differential equation in actual application. It could be on the design of missile going upward. Because if we try to take the graph of this, it should be y equal to e to the 3x. That's it for tonight. So for those who are taking up differential equation, if you like my long video, please click like. If you want to subscribe to my channel is actually at youtube.com/@ProfDavidJ.Reyes. If you want to subscribe to it, please click subscribe. Thank you. Good evening, Los Angeles.